Notes day 3, one-sided limits. Oh, reminder, tomorrow we have a quiz, but the quiz does not include notes 3. It goes up through notes 2. So the quiz is over worksheet 1 and 2. So if what we do today seems crazy, which I don't think it does, but if it does, it's not on the quiz. So you'll be okay. All right, first part of this, I think we should be okay with because we've done this before. So this should serve as a kind of a reminder or warm-up. So why don't you do the first 10 of those questions graphically, and then we'll see where we stand. Okay, so those we're probably pretty familiar with. We've done that before, one-sided limits with a picture. What we're going to do today, well, I hope this statement is true, one-sided limits are obvious, or at least more obvious, maybe that's an important word there, when a graph is provided. But when you want to find a one-sided limit from its equation, it's a little trickier. So here's how we're going to think of this, or think through this. First step, substitution. It's like, all right, that's always our first step with limits. So always, always, always substitution, even if it's a one-sided limit. So 2 plus seems a little bit like a weird number to plug in, but we're going to start by just plugging in 2. And if we get something normal, then we're good. It's when something weird happens that we have to worry about the one-sidedness of this limit. So let's plug in 2. 2 squared minus 4 over 2 squared plus 4. 0 over 8. What's 0 divided by 8? 0. So we're good. That's the answer, even though it's a one-sided limit. Number 2. As x approaches 3 from the left, but on our first go, we don't care about from the left. We only care about from the left if things mess up. So let's just plug in 3. 4 minus 3 over 3 times 3 squared. 1 over 27. Perfectly fine answer. Again, so for all limits, even the weird one-sided ones, substitution is your first attempt. Sine of pi over 3 over cosine pi over 3 plus 1. Let's see, sine of pi over 3 would be root 3 over 2. Cosine pi over 3 would be 1/2. And then we need to clean up the fraction. It's going to be okay as an answer. It's not 0 over 0 or infinity over infinity. So we're good with the answer. We just need to clean it up. And I think following yesterday's style, I'm going to multiply top and bottom by 2. So root 3 over 1 plus 2. Root 3 over 3. Perfectly fine answer, meaning as long as we don't get 0 in the denominator, then we're okay. Or one of those indeterminate forms. So first go, plug in, hope it works, but it won't always. Most of the time, because we don't like the boring ones, we want the fun ones, you will get 0 in the denominator, or one of those weird forms we were looking at the last couple days. So let's plug in 3 plus, or plug in 3. 3 minus 5 over 3 minus 3. Alright, it's negative 2 divided by 0. Well, the okay and no thing suggests this is a bit of a no problem. Like I can't divide by 0. And I know this isn't exactly 0 because I'm getting close to 0. So something weird is going on with this one. So turn the page and we'll talk about how to do the weird ones. And this is one of those days where you're going to look at me like I have 2 heads, I think. So we'll see. If you get a non-zero number in the numerator and a 0 in the denominator, okay, so that's like what just happened there. Some 3 over 0 or negative 5 over 0. Then you have a vertical asymptote. In pre-cal, vertical asymptotes were factors of the bottom that didn't cancel, right? Because they made the bottom 0 when the top wasn't 0. So that's sort of the connection to pre-cal. But what's different today is more than just there's a vertical asymptote, is we have to determine if our answer is positive or negative infinity. So it's D and E, but we need to be more specific on whether it's a positive infinity or a negative infinity. And so that's the big deal with this step, is which infinity is it? Remember that both of these are special cases that are not D and E. All right, but to do this, you're going to plug in a slightly larger number if you're coming from the right, a slightly smaller number if you're coming from the left. All right, minus means subtract, plus means add. So back to that one we were looking at. If I plug in 3, let's start with just plugging in 3. 3 minus 5 is negative 2. 3 minus 3 is 0. So some kind of vertical asymptote's going on there. But I need to know, are we going to positive infinity or negative infinity? So I need to plug in something a little more than 3. So I'm going to plug in, well, what better to represent a little more than 3 plus? So this is where things get a little weird. Right? 3 plus means come from the right, but it also means a little more than 3. Oops, 3 minus 3. Right. Our main concern on these is the zeros. So 3 plus minus 5, let's see, that's negative 2. And it doesn't really matter if it's a little more than 2 or a little less than 2. That only matters for the zeros. All right, this next one is kind of the weird one. 3 plus, so a little more than 3 minus 3. It's close to 0, but is it a little more than 0 or a little less than 0? More, because 3 plus means more than 3. So a little more than 3 minus 3 means you got a little bit left over on the positive side. So this is weird math today. All right. We already know that negative 2 over 0, that's going to infinity. But now we can talk about the sign of that infinity. Because I've got a negative number in the top and a positive number in the bottom. I mean, it's close to 0, but it is positive. So that would be a negative infinity. Because negative over positive is negative. So the 0 in the bottom makes it infinity. The sign is the tricky part. Let's do number 5. Plug in, let's start by plugging in 4. So don't worry about the less than 4 at first, just plug in 4. 4 minus 5 is negative 1. 4 plus 2 is 6. 4 minus 4 is 0. Okay, so something crazy is going on. We've got a vertical asymptote. We would know that, like even from pre-cal, without the limit thing, there's a vertical asymptote at x equals 4. But now we want to get a little more specific and figure out on the left of 4, are we positive infinity or negative infinity? So let's plug in a little less than 4. That looks weird. 4 negative minus 5, 4 negative plus 2, 4 negative minus 4. The only numbers we're really worried about are the zeros. So 4 minus 5, we can still just say that's negative 1. 4 plus 2, that's still 6. It's the zeros that we got to be real careful with. A little less than 4 minus 4 is close to 0, but is it less than 0 or more than 0? Less than 0. I mean, if you're stuck, like pick an actual number that's less than 4. 3.9 minus 4. Oh yeah, that would be negative. So 0 in the bottom means infinity. But what about the sign of this one? Is it positive or negative? Positive, because I got a negative in the top and a negative in the bottom. So positive infinity for number 5. All right, why don't you try number 6? I don't want to do them all. I'll let you try that one. Works the same way as the others. You can see that 2 is going to make that guy be 0. So I know it's infinity, but I'll leave it to you to figure out if it's positive or negative. Because 2 minus a little more than 2, like 2.1. Like, oh, yes, that would be negative. So a little less than 0. Right? 2 minus more than 2 puts you into the negatives. 0 in the bottom means that my answer is infinity. And then I check out the signs. There's only one negative sign, so we're going toward negative infinity if we're coming from the right, approaching 2. So a little bit weird with the 2 plus, 3 plus, 3 minus, that sort of thing. For some functions, now I don't know how many functions this really is, but you can sketch a graph to know the limit, assuming you know what the graph looks like. Do you know what the graph of 1 over x looks like? It's one of the parent functions that we're supposed to know. Might want to give me the hand signals for the... maybe. I can't tell what quadrant you're drawing that in, but... like that? Is 1 over x? So if it's simple enough and you can just sketch a picture, well then you changed it from an equation problem to a graph problem, and most people are better at the graph problems. So as x approaches 0 from the left, that would be on this side, we're going toward negative infinity. So that's kind of a reminder of, if you can graph it, you can change it from an equation problem to a graph problem. The trouble is, there's probably not a whole lot of them you can graph, at least without doing a whole lot of work. All right, this next statement is like double problems here. For other one-sided limits, so one-sided limits are kind of tricky, you might get an indeterminate form after substituting in the x value. That means 0 over 0, infinity over infinity. So we didn't see that. We just got 0 in the bottom, which meant vertical asymptote. And we just had to figure out positive or negative infinity. But if you get 0 over 0, then you got to go back to those other algebra techniques that we did the last couple of days. So it's still substitute, and then algebra, and then substitute again. But this time you're substituting 3 plus or 4 minus or whatever. So all the rules still apply, but this is kind of double problems because you got to account for the one-sidedness and the weird algebra-ness of a problem. We don't give you very many of those because those are a pain. And obviously we didn't even do any examples of them. All right, when x is going to infinity, that is looking for horizontal asymptotes. And we're talking about, or we're considering, the highest degree in the numerator, highest degree in the denominator. We had a goofy saying for horizontal asymptotes, if you remember it. And maybe the bigger on top, bigger on bottom stuff might jog your memory. You remember what I'm referring to? The flower power stuff is the exponents. So it's not that. Well, I mean, yeah, this is exponents, but that's which exponent is the power and which is the root. So it's not that. This has to do with bigger on top, bigger on bottom, Bigger on bottom.
Yeah.
Do you remember what the rest of this was? Bigger on bottom was 0. Bigger on top, slant. What was the last thing?
Yeah, Bobo Boss.
Bigger on bottom, bigger on top. So what's the other case? If it's not bigger on bottom or bigger on top, they're equal. But that's not what's equal. Starts with an E. The exponents are the same, and you'll divide the coefficients. Obobots each DC. Do you remember that enough, or do you need to write out the words for those? Bigger on bottom, 0. Bigger on top, slant, which means there is no limit, like it's going to infinity. DC, divide the coefficients. You don't even have to remember that, because you can look at the picture, you can look at the equation, and so as x goes to infinity, the most important term would be the one with the highest power. So that would be 4x cubed in the top, 5x cubed in the bottom. And if you're plugging in a gazillion, or really even if you're plugging in 10, the rest of those terms aren't going to matter a whole lot. This is really going to be similar to 4x cubed over 5x cubed. And what's 4x cubed over 5x cubed equal to? 4/5. So that's the each DC case, but you don't have to memorize the silly saying. You can just look at the biggest power and kind of go from there. The answer is 4/5. Again, if you like the saying, that's the each DC case. Number 9. Let's see. The highest power in the top is the x to the 5th. The highest power in the bottom is 7x cubed. So at really big numbers, this thing is approximately negative 2x to the 5th over 7x cubed. Let's see. At really big numbers, well, then the x's could cancel, and we get negative 2/7 x squared. And if I plug in infinity to that, negative 2/7 times infinity squared, that would be negative infinity. That would be the slant. There's not one. It's bigger on top. We're headed to infinity. I don't know that the saying is really helpful anymore. I think you're just looking at the biggest powers and go from there. Do be careful, though, because we like to put them not in the right order to just mess with you. So what's the highest power of the numerator of number 10? Well, on the top part is x to the 5th, and on the bottom part is that 7x to the 6th. So this thing is headed toward x to the 5th over 7x to the 6th. All right, does it make sense why we can ignore the other? Because if you plug in a million, right, a million to the 5th is really big. Subtracting 19 is nothing. It's insignificant. Well, here the x's will reduce, and you'd have 1x in the bottom. And if you plug in infinity, 1 divided by a really big number is, right, if you take your $1 in your pocket and you divide it up equally among everyone in the world, how much does everybody get? Roughly 0. Right? If you're going to divide up all the money you have among everyone in the world, pretty much everyone gets 0. That's the Bobo case if you want to stick with the Bobo bots eats DC. Bigger on bottom 0. Bigger on top is a slant asymptote, so it doesn't approach anything. Exponents are the same. You divide the lead coefficients. If you don't want to remember the saying, then you just think about the highest power in the top and highest power in the bottom. Luke?
So if you just recognize that, like, the Bobo one or whatever, if you just recognize that the bottom is bigger than the top, you just put a 0?
Yes. So for most of these, you don't even show the work that I showed. For most of these problems, you're going to get to the point where you're like, yeah, that's bigger on the bottom. So if I'm infinity to the 6th in the bottom, that's bigger than anybody else, we're headed to 0. And there's really no work to show. Even on the divide the coefficients, you see that they're both x cubed, so you know that what matters is the 4/5. Well, there's your answer. So yeah, there's really, I'm okay if you don't show any work on those. That is fine. I want to give you another, it's the same thing as Bobo Bots Eats DC, but it's the one that calculus teachers use more often. Top no, bottom O equal co. It's the same thing. Top, this means who's bigger. Well, if it's bigger in the top, then that's a no. If it's bigger on bottom, that's an O. If it's equal, use the coefficients. The trouble with top no, bottom O equal co is that people will memorize that and they don't memorize when to use it. It's only if x is going to infinity. So I should box that in as part of the. So if you like top no, bottom O equal co, that's fine, but please only use it as x goes to infinity. Because some people, they just really embrace that top no, bottom O equal co and use it for everything. No, I mean, I'm glad you remembered it, but only as x goes to infinity. I don't know. Probably the safest way is forget the silly sayings and rhyming things. Just look at it and use your math brain and think about what's going on. That's probably the best and safest way to go. All right, today's assignment is worksheet 3. One-sided limits algebraically. It's only 12 questions. And you might want to start with 10, 11, and 12 because those are the infinite ones. So those are the ones that require very little work. That's the ones you can look at and get right. Prior to that is where you got to plug things in and be careful with the 0 plus, 0 minus thing.